Okay, let's get started. My name is Marti Bolivar. I work for Nordic Semiconductor, and this is Zephyr Devicetree Mysteries Solved on day 3 of the second Zephyr Developer Summit. Here are a few things that I hope are true about you. The first one is that you know Devicetree, you know, the language a little bit. There are places to start if you do not. Second is that you have taken a look at the Zephyr Devicetree.h API. Maybe you've used it or one of the APIs that are derived from it. And the third is that maybe it didn't go exactly the way that you planned. You know, sometimes the error messages are a little confusing. I want to tell you why these things are the way that they are. There are, unfortunately, some trade-offs that we had to make, and I want to explain the internals to you in a way that will hopefully help you understand them and also be able to deal with them a little bit better while you're developing. Your first thought would be, perhaps, why don't we define a nice structure-based API with, you know, a definition for a node and a nice hierarchy and an API that operates on it and some nice type checking and all these great things. Unfortunately, there is a good reason why we didn't do it this way. And it's resource constraints. You know, this is how other platforms do it. This is how Linux does it. But for us, we can't do that. You know, we have targets that have tens of kilobytes of text, and the entire device tree for many, even small targets, is quite large when you serialize the whole thing. Further, the text to tree walk would be wasted, essentially, since as a library operating system, the entire device tree is known at build time to your application. And third, there's a runtime penalty associated with walking the tree. And so when your clock speed is in the megahertz, you know, that must matter a lot more. You know, that there are latencies, there are startup times. So this was just considered, but considered unacceptable. So that's why we have this crazy mess. Instead, what we do is we combine information from the device tree specification, from the Zephyr device tree bindings that are data files that are associated with Zephyr or your application, a bunch of magic in the build systems that I won't get into, and macrobatics, which is a much more polite term for what my mentor, who is just now evaluating Zephyr, my early embedded mentor when I just got started, called level 10 C preprocessor macro. I won't say it here. Okay, so the device tree specification, you know it, right? That's fine. We won't get into that here. Device tree bindings are basically schemas for nodes. I get a lot of questions. There have been a lot of questions in the chat at this conference and various times, like, why do we need bindings? What does it serve? What purpose? And it's basically a description of what the node may contain. And so the build system needs to know this, not only to validate that the tree is structured properly, but also to, as we will see, perform the conversion from the device tree source format to the C language in a type-safe way or in a type-correct way. So that's why we have them. And there's a link to more information about it in the documentation there. So this is about the level of detail I want to get into with regards to the build system magic. Like, don't worry about the magic in the middle. Just understand that your bindings and your device tree source go into the magic and out-pop a bunch of generated header files in your build directory. And there are a few of them. I want to cover what they are and what they do. Device tree fixups is basically legacy at this point. It's quite old, but it's basically free to continue to support. So even though it's been deprecated for several years, we keep it in there. You may see it. You can ignore it. Device tree unfixed.h is your device tree. That is your device tree. But it's represented as a C header using information from the bindings as interpreted by the magic in the build system. Finally, device tree extern.h is a declaration for every struct device in the device model, not a device tree mode, but like node, but a real struct device that might exist from your device tree. So at magic time, we don't know how many devices there are because we haven't built the code yet. We don't know where they are, but we know how many there may be because we have the entire device tree. So we sort of pre-declare all of the possible ones, and we put them in this header, and I'll show you how that works later on. So those are the 3 files that you'll see output, and it's kind of important to know what the last 2 are and what they contain. And the first one I want to talk about is this unfixed file, I think. Before we get there, I want to do like a little bit of show and tell in terms of macrobatics, just to make sure that we're all on the same page. here's a pretty simple macro. Let's do a warm-up, right? It's morning. Let's warm up. Paste. It takes two arguments, A and B, and it pastes them together as tokens. Okay, fine. So if I say paste foobar, what will I get? Well, I will get a single token, foobar, right? Now, the results of token pasting are recursively macro expanded again. So if foobar is already something, then this whole thing becomes that thing. Clear as mud, right? But the important thing to remember is that the results of a macro expansion are then sort of recursively scanned for macros to expand again by the preprocessor. So that's a good warm-up. Let's introduce another layer of indirection, where now we have a paste2 macro in between paste and the actual hashtag that does the token pasting. So since the formal arguments of a macro expansion are themselves macro expanded before they're substituted into the body, this is allowing me to force expand A and B before pasting. And then I will expand the result. So now paste foobar is paste2 foobar. But if bar is baz, then actually that's foobaz, not foobar. And if foobaz is something else, then that gets expanded again. Okay. Feeling limber? Here we go. Doing a backflip. All right, we're going to keep paste and paste2. That's the same. Now we're going to add this interesting little fooeyes macro that just pastes foo underscore onto whatever you give it. So, for example, if we say bar is baz and we fooeyes bar, then we get foo little baz, because we are macro expanding bar before we paste. Now, if that's all that foobaz is, it's just a token. If it's not defined to anything, then that is the result of preprocessing, and that's what gets fed into the compiler at whatever point in your translation unit it's looking at. So this can just be a token, right? It doesn't have to be anything. It's just a token. Anything more specific than a token, let's say. So now let's combine the two and see where this is headed. So if we paste fooeyes bar with underscore 1, and I have a couple of additional helpers, I will get foobaz, which is what fooeyes bar is, pasted with 1, and then I macro expand that again, and I get this integer value. Similarly, if I use a different argument in the second slot in paste, I get 43, this other thing. So you can see here that in the preprocessor, if I'm sort of careful about how I paste and how I organize things, I can kind of create what almost looks like an array of elements. And this slide is actually kind of the heart of the Devicetree API. There's nothing that you need to understand about Devicetree.h that is not on this slide. So it's not super complicated, but there is just this sort of like, and then I macro expand, and then I paste, and then I macro expand again thing that you kind of have to keep in mind. Okay, so that's kind of all the prep work that I want to do. Now I'm going to move on to some actual implementation details. We're going to talk about how Zephyr DTS, your device tree, gets converted into its header file representation. Here's a really simple device tree. I've got the root node, which contains a parent and a child node. The parent and the child nodes have different properties. Both of the properties are named size, but they have different values, 3 and 4. So wouldn't it be great if we could just say in the preprocessor, like, hey, give me the size property of node parent as strings, right? Strings would be nice because those can be pasted into error directives, and that will give us really nice compiler diagnostics. The problem is the quotes. You cannot strip quotes from a string literal at preprocessor time. So it does not work. We can't do it this way. We really tried. If this has occurred to you, and you want to extend the C language, go ahead. Or, we chose macrobatics. We chose violence instead. Let's see how that works. I want to talk now about node identifiers, because node identifiers are something that's mentioned in the device tree guide, and really they're left very intentionally vague. Like the actual thing that a node identifier is an implementation detail, but we're going to talk about that implementation detail today because it's important. So you may recognize this dtPath macro from the device tree API, and dtPath parent, if you know the API, is a node identifier for the node with path/parent. And similarly, dtPath parent child is the node identifier for a node with path /parent/child. And that's what they expand to. They expand to these kind of random-looking tokens. But the really interesting thing is that there's a mnemonic here and there's a system here. So DTN in both means device tree node. So that's just a mnemonic. You can see that whenever you see DTN, that means that it's a node identifier, right? And then anytime there's a slash, which is not a valid character in a C token, we just use a capital S. And if you've ever wondered why we always ask you to lowercase and underscore the arguments to all these devicetree.h macros, the reason why is so that this kind of uppercase, lowercase convention results in a consistent encoding that doesn't allow for collisions between two different nodes or nodes and different properties. So this is what node identifiers are. Like anytime you construct a node identifier using devicetree.h, it's through some sort of twisted combination of pasting and macro expansion, it's going to expand into something that looks like that. But this is not a value, it's just a token. So let's summarize node identifiers. DTN is device tree node, /foo/bar, and hopefully you can kind of read that a little bit more clearly now. We lowercase and underscore everything from the device tree so that we can use this encoding in a consistent way. In the previous iterations of our journey with device tree, we had some problems where it was possible for a property at one level of the tree to collide with another node, and so this new encoding that's been here since Zephyr 2.3 prevents that, but it requires this lowercase and underscore convention, and that's why. Okay, so again, I really want to hammer home that they're not values, they're just tokens. This isn't defined to anything anywhere. But we can use them to get the values of properties without any of the overhead that we are trying to avoid, right? So the whole point of this exercise is that we want to use device tree within Zephyr because it's a very successful and very expressive configuration language, but we have these incredibly tight resource constraints that force us to do a little bit of extra work. So the way that it works is that if I look at this size property, what you will have in device tree on fix.h is a macro that encodes its value. And the beginning of the macro is the node identifier, and then you have this capital P, which means property, and then the lowercase and underscores name of the property. So you could write this in your application if you had this in your device tree and suitable bindings to make it all work, but that's kind of obviously clunky, and you're sort of hard-coding paths, and it's much nicer to be able to use things like aliases, instance numbers, and node labels. And so that's why the devicetree.h API exists. It's to allow you to have that indirection and that abstraction, while at the end of the day just coming down to a bunch of macros that get expanded and don't have any additional overhead. Let's see how it works. Like I said, to summarize, we need type information from the bindings. The build system is going to use that to encode node ID p baz macros for every property baz. But what is it going to define these to? It needs information, right? So technically within a device tree, it looks like from the source file, like we have a lot of type information, right? We have these like p handles and everything, we have hex numbers, but actually in the specification, from the perspective of like what is a device tree, every property's value is just a bag of bytes. Like we have no additional information. All of those source encodings are just syntactic sugar for byte arrays, because it was intended to be a binary format from the beginning. And so the bindings give us the types that we need in order to represent these properties in sensible ways as C literals. So that in turn allows us to take only what we need and save it in our drivers, and anything that's not compiled in, that information gets thrown away. Very concretely, when I define this parent node to DT path parent, so now you see I have a node identifier, and that's just DTN S parent. But I have a shorthand for it, which allows me to avoid encoding those implementation details in my application. Now when I use the DT prop macro, I give it the node identifier, and I give it the property that I want to read. And what's going to happen is that, again, through kind of a convoluted series of expansions and pasting and recursive expansions, it's just going to expand to that literal value without any additional overhead. So that's how it works in the real world. You may be wondering how this works for other things. And one thing I want to say, and the reason why I think it's okay for you not to understand what's going on in that magic box, is that there is actually documentation up for the complete encoding of a device tree as it will appear in devicetree on fix.h, and that's the link for 3.1. So for example, for properties, you see at the bottom, that's the only kind of line that has any sort of specific meaning, but it's the definition for a non-terminal node in a BNF grammar. And so this grammar is written according to a syntax that has an RFC, and if you load the link, you'll get all the details. But the important thing is that it tells you, what is this sort of macro, this generated macro? What is it about? What, some additional context about it, and the components that comprise the entire macro and its meaning within the program. So this is potentially a very useful thing for you. If you get an error message with like this macro that you don't understand, you can look for like what is this related to, and then that can help you map it back to your device tree to overcome the limitations of the C preprocessor that we are dealing with. So if anything is vague in that section of the documentation, please let me know. I've done my best, but obviously documentation can always improve. And if something is unclear to you, bug me on Discord, open a GitHub issue, and we'll try to keep improving it. So that's your device tree in a C header. Now let's talk about devices. I mentioned earlier that there's a couple of important headers. One of them is your device tree as a C header, and the other one is all of the potential devices that may exist as a result of that device tree. And all those potential devices are declared in divacetree_extern.h. And I have here on the top roughly what it will look like. I've simplified it so that the slides are easier to read a little bit, and then kind of on the bottom what it expands to. So it's just a bunch of declarations of extern construct devices, because devices go in ROM. And then I just give a bunch of what you may recognize now as node identifiers to device DT name get. And through our usual circus of pasting and expansion, this becomes just a list of declarations of global variables. And they're indexed by this ordinal number. So this is the device which comes from device tree ordinal number 0, and we declare it. And in this case, it corresponds to DTN, which is the node identifier for the root node, which, okay, there's probably not actually a struct device for that, but maybe there is. We don't know. The script is dumb. It doesn't try to figure that out. But then, maybe this LED node does have a device if you've built the right GPIO LEDs device driver. And so this declaration will correspond to a global variable that actually exists and is available to your application. So we just get all of them. Now, you may be wondering why this is necessary. Like, this looks a little complicated. It's a really frequent FAQ. Like, why do we have these ords? Like, for example, why didn't we just keep the node identifiers in here? I want to talk about why. And the reason is that it broke user space. That's how it worked at first. But if you see what it starts to look like, these devices would have very long names. And that ended up breaking certain limitations in our user space model. So you can download the slides for the talk, and you can look at this commit, and that's the short log. So this is the workaround that was adopted to enable the same kind of encoding of the global variable names to work both in user mode and without user mode enabled. So now what happens if you get one of these famous like device DTS ord or some random device mishmash undefined reference error? So there's two possibilities, which you may be able to anticipate now based on what you know about divacetree_extern.h. The first issue is that can happen is that the device was simply not allocated. Right, so you've declared something that just doesn't exist. And of course, it'll be an undefined reference, kind of by definition. The other possibility is that you have a typo. And the two possibilities generally can be told apart quite easily based on the error message. And I'll show you how. So let's do the first one first. If you see undefined reference to, here for my example, device DTS ord 105, now you know, okay, that's node number 105, right? How do I find out what node that is? Well, you can figure that out because device tree unfixed is your device tree. And it says, if you open it up, you'll see there's a bunch of comments. It's actually very nicely laid out for generated file, if I do say so myself. And you can see the ordinals that are associated with every node, and you'll be able to figure out which node the device is not allocated for. And once you know the node, you can figure out the driver that should be handling that node, right? You can look at the node and say, oh, this node has compatible Nordic NRF SPIM. Okay, well, that's my SPIM driver. Like, that really should be allocating the node. Like, why isn't it? Maybe the driver's kconfig is disabled, right? Maybe config spy is N, and I need config spy to be Y to get my SPIM driver. Maybe the node is not enabled, right? If I look at my node and I say, oh, it's disabled, like, well, okay, then of course the driver won't allocate a device for it because that's how it works. So these can be handled in this way, like very consistently. Now, of course, you may end up with this device DTS or dog's breakfast. And the thing that happened here is that we pasted something. We tried to get the ordinal of a node or a property or something vaguely indirectly through any number of twists and turns through the device tree, but we ended up somewhere that doesn't exist. So that's usually because of a typo. And you can see here, it's like I'm trying to expand the device with ordinal, but there's a typo somewhere in the macro soup that made and it happens to be right here. It should be GPIOs, not GPOS. So you can kind of scan through and look and try to map that back to where in your source file you may have a typo. And again, this is kind of unfortunate, I know, but like I'm really open to suggestions for how we might be able to do this better while still making the no overhead guarantee. This is kind of the best we've been able to come up with, but please, by all means, save us all. So if you want to, kind of cut through the noise of your source file, there's a troubleshooting guide that explains a variety of tactics and kind of your last resort, but often I will just reach for it first because I think it's really useful, is to just look at the preprocessor output. And this is really easy to do with Zephyr. This is the section that I'm referring to on that troubleshooting page that you have the link to on the previous slide. You just, run west build with an extra option, and that's going to leave the result of the preprocessor output in your build directory. So you can just find, if you're looking for, where's the preprocessor output for main.c, look for main.c.i in your build directory. Then you clean it up, run a formatter on it, and open it up. And often that is a really helpful way to figure out what's going on, especially now that you're kind of armed with a little bit more about how this all fits together, and you'll be able to read through the devicetree.h API a little bit more clearly to see how this is all working. So this is kind of my last piece of advice for you. I'd like to open the floor for questions. Otherwise, thanks for your time.
So for the for each macro,
Yeah.
there's very explicit documentation for that particular for each that's unordered. So the ordering is not fine, which is great, but the other for each macro, like for each child, do not say whether it's down ordered. So I'm wondering, not that documentation guarantee of the other for each order.
Yeah, so the question is, there are several macros in the devicetree.h API that allow you to iterate over a certain set of nodes, like for every instance of a certain compatible, or for every child of a certain node, and sometimes the order is clear. We've documented that when we iterate over nodes by instance, there are no guarantees, essentially. And the question is, for other things like for each child, what is the order? The order is as it appears in Zephyr.dts. So I will document that. Now, the thing is that I can't say what that will be because it will be heavily modified by overlays, right? So if you delete a child and then add it back at the end, you're messing with the linked list in a way that will result in something, but the iteration order will be consistent with what's in your device tree.
The implication was, I guess, yes, thank you for that, and it's through implication, correct ordering, following, it says never explicitly that.
Yeah, okay, I'll fix that. Thank you.
A question about device tree as inbuilt to have dependencies, and you can depend on different nodes in the order of how they appear in the tree. So if you have like a device on an I2C bus or something, they're in direct dependency. But currently Zephyr is not doing anything with those dependency relationships. And for example, if I enable a device in my device tree, which is on the bus, it's not being used, most of the time it's going to work. Is there like any plans to support it, or is it possible with the current device tree macro expansion to do this kind of dependency relationships?
Yeah, so the question is basically about ordinal numbers. The thing about ordinal numbers is that it's like a fancy word, right, ordinal? But there is actually an ordering, and it's a dependency ordering. So if you iterate over the nodes in dependency order, if you iterate over the nodes by ordinal number, you are iterating over them in a dependency order, like in a topological sort of the dependency graph. Now the question is, why is it not used in the device model, right, to make sure that we don't initialize a bus device before the bus or something like that? And the short answer is that Devicetree got added to Zephyr after the device model already existed, and so this would be a very difficult change. We feel your pain. We definitely like the static levels and priorities. A lot of that information is really available in the device tree. Now, the device tree exposes this. So you do have this information in Zephyr Devicetree.h, and there is a way to capture this in your struct device within the device model API. The missing pieces are to refactor every driver in the world to not use a static initialization level and priority, but to get this information from Devicetree. And I hope I don't have to explain why maybe we haven't had time to do that yet. Yeah. Next time. Patch is welcome. All right. Any other questions? Okay, thank you.